Linear regression modeling is less effective in the case where dependent variable is binary and of the form like yes, no or 0, 1 kind of variable. Such dependent variables are called limited dependent variables or binary choice variables. A simple OLS ordinary least square regression model approach is referred to as linear probability modeling approach since the predicted variable is in the form of probabilities. However, these linear probability models are inadequate to satisfactorily model limited dependent variables such as 0, 1 or yes, no. These limited dependent variables are often modeled using logit-probit class of models. We'll discuss the logit-probit class of probability distribution functions that provide theoretical underpinning to these classification algorithms. Moreover, the predicted probabilities from logit-probit models require thresholding to convert them into ones and zeros that are comparable to the observed data. We'll also discuss a very important and comprehensive parameter of model performance, that is classification confusion matrix. Also, we'll visualize the model performance under receiver operator characteristic curve and compute the area under the curve to examine the model performance. Lastly, we'll interpret the parameters from the logit-probit model estimation. In this video, we'll introduce the classification problem with a background to discrete choice variables or qualitative response variables. Discrete choice variables or limited dependent variables or qualitative response variables as they are called are like 1, 0 or yes, no kind of variables. It is very difficult to model these variables through linear regression models as we have seen. Let us examine the following questions. Why do firms choose to list their stocks on NSE or BSE? Or why do some stocks pay dividends while others do not? Or what factors affect large corporate borrowers to default or not default? What factors affect choices of internal versus external financing? Notice that in all these questions, the dependent variable, the fact that is predicted or determined, is in the form of yes, no or 1, 0. That means there are two choices. And these choices can be modeled in a regression model through yes, no or 1, 0 kind of format. For example, one can put the choice of listing a stock on an SC as 1 and BSC as 0, or paying dividend as 1, not paying as 0, or defaulter as 1, non-defaulter as 0. So these choices can be modeled in a linear regression model mathematically by coding them as 1 or 0. Let us understand this through a simple example of a credit scoring problem in banking. In banking, there are often loan applications that default or not default. If you want to know or judge the creditworthiness of a particular application, there are certain attributes that you would like to examine. For example, you would like to examine net worth of the borrower or his or her income. Now, suppose you want to train a credit default scoring algorithm or a classification algorithm, you would like to have a label data. The data being labeled as defaulter. In this case, these red dots or circles, solid circles, are defaulters. Let's call them defaulters. And the blue ones are non-defaulters. So you have the labeled data and you also have their features as net worth and income. Now, using these labels and these features, you would like to train your algorithm. There are different ways to do it. For example, if you're given only net worth, you would have trained your algorithm at different levels based on the level of net worth and tried to see which of these levels classifies or categorizes the data best between red and blue observations. Similarly, if you are given only the income feature, then you would have tried different levels of income to classify data according to its labels and the most efficient way possible. You obviously would want to use both of these features and then classify. For example, in this case, this kind of algorithm appears to be most suitable, and therefore in future, if some data is available to you where the point is here, then you would like to classify it as defaulter, and if it is available here, then you would classify it as non-defaulter. To summarize this discussion, we noted that the fundamental aspect behind the classification problem is the presence of label data, where data is labeled into two or more categories. For example, here we saw defaulter or non-defaulter. So data is labeled into two categories and you are given certain features of data. For example, in our case, net worth and income were some of the features. Features can be demographic aspect of individuals, taste, preferences, various kind of features can be given to us along with their labels. Now, a classification algorithm would be some kind of algorithm that using these features would try to label the data accurately, higher the efficiency of the algorithm, that means its ability to classify accurately the data into its labels correctly, the better its efficiency. In this video, we'll introduce a simple approach to modeling discrete choice variables or limited response variables, which is called linear probability modeling, LPM. Recall that regarding such limited dependent variable modeling, we said that the dependent variable is of the form of yes, no, or 1, 0 kind of variable. We'll start by modeling or introducing the simple linear regression approach to deal with such models, and this simple linear regression approach in this context is called linear probability model. This is the most simple approach to deal with the binary dependent variables, but as we'll see in the next video, it is fraught with its own issues. But let's introduce this problem. It is based on the assumption that the probability of an event pi is linearly related to a set of explanatory variables x1i, x2i, and so on up till xi, xki. So the problem formulation would look something like this, where pi, the dependent variable, is essentially the probability of an event happening y equal to 1. For example, if you're talking about bank default, default versus no default case that we discussed in the previous video, we assume that, let's say, if default is happening, then in that case the event is coded as 1. So the probability that default happens, or the variable y takes value of 1, this p of yi being 1 is noted as pi, is modeled along the set of independent variables x2i, x3i, and so on, and their coefficients which reflect the impact of these variables as beta 1, beta 2, beta 3, and so on, in an identical manner as we would model the simple linear regression problem. Please note that in such models, the actual probabilities cannot be observed. So the estimates, which essentially we model in the form of probabilities, have to be converted into zeros and ones. So this is one problem, that you do not observe probabilities. What you observe is the event happening, which is 1, or not happening, which is 0. For example, consider the relationship between a company I and its ability to pay dividends. So whether a company I pays dividends, let's call it event y equal to 1 if dividend is paid, and equal to 0 if it is not paid. Now let's model is this event in the form of, or its relationship with its market capitalization xi. So xi is, here is the market capitalization of the firm, which is captured by this relationship is captured by this coefficient beta 2. Here essentially what we are modeling when we write yi equal to beta 1 plus beta 2 xi plus mu I, essentially we are modeling probabilities, but those probabilities will not be observed. What we observe is whether yi equal to 1, dividend has been paid, or 0, which is dividend is not paid. Let us clarify this linear probability model in more detail. So what we just saw, that is yi equal to beta 1 plus beta 2 times xi plus error term, is basically, here in this model what we'll get in the form of beta 1 plus beta 2i is the conditional expectation. Recall our discussion on simple linear regression modeling. It is the conditional expectation of yi given xi, that means expected value of yi given xi. And in this linear probability model case, it can be interpreted that the event will occur given xi, that means conditioned upon xi. The probability that event will occur is given by this expression. So probability that event will occur, what is that event? yi equal to 1. That means dividend is paid, which is represented by y equal to 1, conditioned upon xi. The probability, this is what we are estimating, and in the simple linear regression or even multiple linear regression, if you remember, we called it expected value of yi given xi, which is this. So here the probability that event will happen is nothing but simply the conditioned upon xi, the expected value of yi. So we can also write this expression in this form, expected value of, we have already seen this expression in the context of simple and multiple linear regression modeling, that expected value of yi given xi equal to beta 1 plus beta 2 times xi. And here the assumption is, as we have seen earlier in this linear regression modeling case, the expectations of error term is 0. To summarize this video, we introduced the linear probability modeling approach to modeling what we call binary response variable or discrete choice variable. For example, if yi is whether a company will pay dividend, that means y equal to 1, or not pay dividend, which is y equal to 0, we model this kind of binary response variable. We model this kind of binary response variable or discrete choice variable with the help of simple linear probability modeling by this kind of expression, where we said that the probability whether yi equal to 1 given xi here is our independent variable, can be modeled in the form of following expression: beta 1 plus beta 2 times xi. Here we also drew parallels between this approach and simple linear regression modeling approach, where we said that the dependent variable is also written in the form of expectation of yi given xi, which is equal to beta 1 plus beta 2 times xi, where this expectation of yi is nothing but simply the event happening, that means the probability of event happening, that means y equal to 1, the probability that this event will happen. So we are simply modeling probabilities in the form of linear regression model. In this video, we'll examine some of the issues with LPM, that is linear probability modeling. Recall our discussion on non-normality and heteroscedasticity on the video topics related to heteroscedasticity and normality in linear regression modeling. There are two possibilities for the event yi, that is our dependent variable, either 0 or 1. Remember, we said that if yi equal to 1 as per our regression model, it has a probability of pi. Basically, pi, if you recall the discussion in the previous video, pi was the probability that yi equal to 1. And the remaining, because probabilities have to sum up to 1, 1 minus pi is the probability that y equal to 0. Let us calculate the expected value of yi given xi. This is quite simple. If you recall our calculation of expected value, it is 0 with 1 minus pi probability and 1 with pi probability, and therefore the expected value should be equal to pi. 0 into 1 minus pi plus 1 into pi, which is equal to pi, which is our conditional value of yi given xi. When your dependent variable is of this nature, this kind of model is fraught with several econometric issues. To begin with, notice when yi equal to 1, essentially your error term is of this nature. Why? Because yi equal to beta 1 plus beta 2 in our simple model xi plus error term. So if yi equal to 1, this is the form of your error, and if yi equal to 0, you can rearrange and your error term will be like this. Now this kind of error, the nature of error when formula is of this form and resulting form is this, error is not normal anymore. This kind of jumping behavior from this to this. So there are only two options for error, either this or this. So your error term is not exactly normal. This should be clear looking at these values. When y equal to 1, error is of this form, and y equal to 0, error of this form. So there are two very distinct behavior of error terms. However, it is still not a problem with large samples. So if your sample is large, this normal distribution of error term is still not a problem. I request you to look for a term called CLT, central limit theorem, which says that in large samples, the normality of error term is ensured, because if you have sufficient amount of large sample, then in repeated samples your sample estimates of beta 1 and beta 2 will be normally distributed, even though your error may not be normally distributed. But if you have large samples, in repeated sampling your estimates of beta 1 and beta 2 will be normally distributed. This comes from the central limit theorem, and therefore central limit theorem or CLT ensures that mu I, even if it is not normally distributed, if you have a large sample, this is not an issue. However, at the same time, notice mu i's are also heteroscedastic. Recall our discussion on video topic on heteroscedasticity in linear regression. Here mu i's, they vary with yi. So either yi equal to 1, then mu I have a separate function, and if yi equal to 0, then mu I has a separate function. It means that mu i's are varying with yi, which is clear-cut violation of homoscedasticity assumption, which means the errors or mu i's are heteroscedastic. And therefore, this can create number of issues with estimation of coefficients like beta 1, beta 2. Another very critical issue that is getting violated here is the fact that expected value of yi, which is nothing but the probability pi, should be between 0 and 1 because this is probability and by nature it should be between 0 and 1. However, if the model in the linear probability model, there is nothing that stops this probability to be greater than 1 or less than 0. Let's look at an example here. So if we have yi as a function modeled like this, let's say our estimated function is minus 0.3 plus 0.012 xi, and recall in the previous video we noted that here xi is the market cap and yi here is what we are modeling is the probability whether dividend is paid or not. So if dividend is paid, then y equal to 1. If dividend is not paid, then y equal to 0. And essentially we are modeling that probability of dividend being paid. In this function, if the resulting function of this form, then every $1 million increase, xi is in million dollars, so every $1 million increase in the capitalization indicates that the probability that firm will pay a dividend increases by 0.012 or 1.2%. In this expression, if x is less than $25, then this value of the probability value that is computed from this expression is less than 0, and if x is more than $108, then the probability value pi will be greater than 1. Now this is a very problematic case where probabilities that are obtained or estimated from the regression are less than 0 or greater than 1. Why so? Because a probability of less than 0 indicates that small size firm for which this probability is coming out as less than 0, recall that number $25 million, that means these firms are rather small firms, they will never pay dividends. And similarly, for all the large firms, pi greater than 1 indicates that they will always pay dividends. Why? Because as a solution, you would rather, as a simple solution to this problem of less than 0 and greater than 1, you would rather put all the observations less than 0 as equal to 0 and all the observations greater than 1 as equal to 1, which means you are essentially assuming that small firms with a certain market cap, in this case $25 million, less than $25 million will never pay dividend, will be pi equal to 0, and greater than $88 million will always pay dividend, that means their pi is equal to 1. This is a very problematic assumption and understanding of the model. Another very critical problem with this kind of modeling is the diminishing utility of R square as a goodness of fit measure. Recall our discussion about linear regression model. We said that R square measures how well the model explains the variation in the dependent variable. Notice in this kind of setting, the values of the dependent variable can be either only 1 or 0, that means they will be at this or this. And therefore, any linear probability modeling like what we are doing here, LPM linear probability model, which fits a line like this, will have extremely high, the error terms will be very high. And therefore, because of such large variation in error terms, the R square will be very, very low. Therefore, R square as a goodness of fit measure will give very poor performance, because by nature of the fit of model, all the observations will be either y equal to 1 or 0, and therefore such large errors will result in extremely poor R square, and therefore the conventional linear probability model is not expected to fit well with the actual observations. Only for very few cases where observations are very close to this point, the fitted point here, close to this point B and this point A, will probably give lower errors, and therefore only few observations will have low magnitude of errors. For all the other observations, the magnitude of errors is extremely large and very frenetic, jumping up and down. To summarize this video, we noted that linear probability modeling approach, that is translating our simple linear regression modeling or multiple linear regression modeling approach to modeling discrete choice variables like 0, 1 or yes, no, is fraught with issues. To begin with, the nature of error is non-normal and heterostochastic by very nature of design of LPM models. Second, the utility of R square becomes very low as a goodness of fit measure. R square doesn't work well with LPM linear probability models. And third, and also very important, that the variable being modeled here is of 1, 0 kind of form, which is modeled in the form of probabilities, and probabilities are restricted between 1 and 0. And there is nothing in the linear probability model, which is an extension of simple linear regression, that stops these probabilities between 0 and 1. So the probabilities can actually extend beyond 1 and less than 0 as well, which is also problematic. In this lesson, in next series of videos, we'll discuss the logit or logistic regression and probit approaches, logit and probit models that are able to overcome the limitation of linear probability modeling, where it produces values less than 0 and more than 1, and also account for other issues that we discussed, that is non-normality and heterodoxy of error term, and different goodness of fit measures in the context of logit and probit approaches that overcome all these problems. In this video, we'll introduce a very important classification algorithm, which is often referred to as logistic regression or logit modeling approach to model binary response or qualitative response variables, or what we call discrete choice variables, such as 0, 1, 1, 0. Recall one of the major problems faced by LPM approach, that it resulted in dependent variable which was beyond boundaries of a probability, that is less than 0 or greater than 1. These logit and also the probit approaches, they try to overcome this problem or the limitations of the linear regression model by transforming the model to a function that is bounded by 0 and 1. And therefore the fitted function as per the logit approach, and also later on as we'll see with the probit approach, looks like a S-shaped curve here, which is bounded on the left side by 0 and on the right side by 1. And the precise function in the case of logit model, the precise function is fzi, function of zi is e to the power zi upon 1 plus e to the power zi. We can also rewrite this equation as by dividing it with e to the power zi, and it will result in 1 upon 1 plus e to the power minus zi. Let us examine this function in slightly more detail. Here, this function fzi is nothing but a cumulative logistic distribution, what we call cumulative logistic distribution, where zi is equal to beta 1 plus beta 2 times x2i and so on up till beta n times xni plus error term. This is a familiar expression to us. This is same expression as we saw in the case of linear probability modeling, only now that we have transformed this into the cumulative logistic distribution or logit function, which is probability of yi equal to 1 is equal to 1 upon 1 plus e to the power minus zi, where zi is this expression. So this is sort of non-linear transformation of the original linear probability model. Let's discuss some of the properties of this logit function, which is pi is y equal to 1, that is probability of yi being 1 in this expression, where this part is zi. So it is 1 upon 1 plus e to the power minus zi. Now if zi, let's look at the asymptotic values when zi tends to plus infinity and tends to minus infinity. If it is tending to plus infinity, this value will become 0, and the overall function, the cumulative logistic function, distribution function, will approach a value of 1. So it will tend to 1 wherever z is approaching infinity. And if it is approaching minus infinity, then this value will approach to infinity and overall expression will approach to 0. So the limiting cases of 0 and 1 are achieved, and therefore whatever the value of this expression zi, which is zi is represented by this expression, the linear function, in variables, whatever irrespective of these values, the limiting cases of probability will remain between 0 and 1. However, we can easily see here that now the model is not linear in parameters. So this is not a linear model, and hence it is not amenable to OLS estimation. At the end of this lesson, we will discuss an approach called maximum likelihood approach. At the end of this discussion, we'll discuss an approach called maximum likelihood approach, or MLE, maximum likelihood approach, which is employed to model and estimate such models. But important here to note that these are not modeled using OLS estimation, because these are not linear models, not linear in parameters. Importantly for us, this model will predict the probability that y equal to 1. For example, we can take an example where the bank loan default, let's say default is y equal to 1, where yi is our dependent variable, which is the probability of default. So this model would predict the probability that yi takes a value of 1. So now that we have said that probability of y equal to 1 is the probability of interest, that is, let's say, probability of default and so on. Probability of non-default can be easily estimated as 1 minus probability of default. Here, the dependent variables x2, x3, and xk and so on, these are our dependent variables. And essentially, this is a non-linear transformation of the model to produce probability consistent result. So that means we are transforming our model, which was originally the linear probability model, into a non-linear model, which provides us with the probability consistent results. To summarize this video, we introduced the logit model or logistic regression model, wherein we transformed our original function into cumulative logistic distribution function, which appeared something like this, where zi here, this zi is of that similar to that linear probability model, which was of this form: beta 1 plus beta 2 x2i and so on up till beta and xni. Plus the error term. The key desirable properties of this function included that this expression, when zi tends to infinity, this expression tends to go to 1, and when zi tends to minus infinity, this expression tends to go to 0, which means now these values are probability consistent. In this video, we'll improve our understanding of logit function and relate it with the odds ratio, which is very familiar with the concept of probability. Let us re-examine our logistic function, logit function here, which is simply probability of yi being 1, which is the event of interest, as 1 upon 1 plus e to the power minus zi, where this expression represents the zi, the linear part of the model. Now recall, if the values of zi, which is this expression, that is this one, is extremely low and negative. So if the values of z are extremely low and negative, then that would indicate the probability of no dividend. Recall our example where no dividend case was probability of y equal to 0. So extremely low values of this expression would suggest probability of no dividend, or another example, probability of non-default cases with a higher probability. So higher chances of no dividend or non-default if this value is very low or negative, because remember 1 plus e to the power minus zi, if this value is very low negative, minus it tending to minus infinity, this expression will become tend to very large, tend to infinity, and overall value will be 0. Similarly, extremely high and positive values of this expression, extremely high and positive values of this expression, which is zi, which means if zi is tending to positive infinity, then this expression, this value will tend to 0 and overall value will tend to 1, which indicate a high probability of dividend payment or default cases, which is of our interest. So remember, in our examples, the cases of interest were defaulters with y, which we classified as event y equal to 1, or payment of dividend, which we classified as event y equal to 1. So a high probability of these events if the value of zi or this expression is very large. Now let us develop this understanding in the terms of our very familiar odds ratio. Odds ratio is nothing but the ratio of, let's say there are two possible events, in this case default, non-default, or payment of dividend and non-payment of dividend. Then the event of interest on the numerator and event of not interest opposite to that interest in denominator will give us the odds ratio, which is probability of y equal to 1 divided by probability of y equal to 0. Now if this odds ratio is greater than 1, then it's obvious that y equal to 1 event, which is either default or payment of dividend, is more likely. While if odds ratio is less than 1, that means event which is coded as y equal to 0, that means either non-default or in some other example non-payment of dividend, is more likely. So this is how we define our odds ratio. So now let us substitute our logit function in the odds ratio. Then remember, what was our odds function? E to the power minus zi. This was our function of interest. So we put this in numerator. This was for py equal to 1, and for py y equal to 0, what should be the relevant expression? That should be 1 minus 1 upon 1 plus e to the power minus zi. So if you simplify this expression, eventually it will work out to e to the power zi. So you can, it's a very simple computation. Numerator divided by denominator. Recall this function, numerator divided by denominator, we get this expression e to the power zi, which is, and where zi is this expression. So if we simplify the odds ratio, by putting the values for p equal probability of y equal to 1, we have 1 upon 1 plus e to the power minus zi, and p y equal to 0, which is nothing but 1 minus p of y equal to 1. So if we put these expression, we get e to the power zi, and therefore odds ratio is nothing but e to the power zi. Or if we take the natural log on both sides, we get ln odds equal to this expression. Natural log we have taken on both sides, left LHS and RHS, so we get natural log of odds as this expression. Now notice, the higher this value, the higher this expression or natural log of odds, the higher the probability that the likely event is y equal to 1. So the higher the value of this expression, the higher the odds in favor of event y equal to 1, and vice versa. That means lower, extreme low negative values of this expression, lower the odds in this expression, this probability, and more odds are in more favor of this event. And this is what we said earlier as well. To summarize, in this video, we discussed the logit function in greater detail. We transformed the logit function and related it to the familiar odds ratio. We already know that odds ratio is the ratio of two events where the numerator is the event of interest and denominator is the opposite event. We found that natural log of odds is nothing but the same linear function, which is zi. So zi, the expression corresponding to zi, is nothing but the natural log of odds, and therefore we simply and very intuitively understood that higher value of zi's, extremely high value of zi's, positive high value of zi's, would increase the odds in favor of the event of interest, which is y equal to 1, and extremely low and negative values would favor the odds corresponding to probability y equal to 0. In this video, we'll discuss the concept of thresholding in the context of logistic regression. In the case of logistic regression or discrete choice or limited dependent variable models, essentially the outcome of the model is probability. For example, remember our dependent variable where we estimated, essentially what we estimated was probability that event of our interest will happen. That was the probability that we wanted to estimate. Probability that y equal to 1. For example, if you remember, recall our bank loan default that we have continued in this lesson. We said that if the application defaults, then that case, which is y equal to 1, if y takes value of 1, we estimate the probability from our regression model, which is the logit which we estimated using logit function of the following form: e to the power minus zi. Now in real life, you would not only want to make prediction about probabilities, but actually what you observe is ones and zeros. For example, 1 may be a defaulter and 0 may be a non-defaulter. So you would like to convert your estimated probabilities using logit, or even if it is a probit or any such model, and convert them into cases of ones and zeros. This requires some kind of threshold value t. This t value is needed to convert your probability predictions into binary predictions of ones and zeros, that is, for example, default or no default. A simple example to build the intuition would be, let's say you select a value of threshold tau. If this tau is, if the value that you obtain, the probability value that yi equal to 1 is greater than tau, greater than equal to tau, then you say that it is a default or the event that is of interest. You can change it also, default or non-default. And in case if it is less than t, if the value, the probability value is less than t, then you predict as a case of y equal to 0. That means you predict it as a non-default case if the probability is less than t. Now an interesting question here is, what should be the appropriate value of tau? What kind of error would you want to prefer? Please notice, given a t value, there is a possibility of making two types of error. One, whether the actual outcome is of non-default but you still predict it as defaulter, which can be considered as false positive. Falsely, you consider it falsely as a case of y equal to 1, that is default, while it is actually a non-default case. And the second kind of error is you predict non-default, which is actually a defaulter. So it is actually a y equal to 1 case, but you predict it as y equal to 0. So you predict non-default. So this is false negative. Let's try to visualize this. So for example, consider there are this is your tau value, and you have some these are all your non-defaulters. Let's call these x's as non-defaulters, and let's consider on the higher side these are defaulters in zeros. These are defaulters. See, I am putting visually them on the higher side because they have a higher tau value, a higher probability of default. I'm associating with them on the higher side. Now suppose you select a very large threshold. Suppose you select a very large threshold of, let's take an extreme threshold of 0.8. So let's say you pick a very high value of t, let tau or threshold, let's say a very high value like 0.8. And since it is a very high value, you will classify a very small fraction as defaulters. So now in this case, what about these default cases? Because you have taken a very high value of tau, while you would select certain number of cases which are defaulters, there are number of defaulter cases, zeros here, which will be classified as incorrectly classified as non-defaulters. So a large number of defaulters will be incorrectly classified as non-defaulter. That means with a large probability you will classify a large number of default cases as non-defaulters. So a number of false negatives will be occur. So this is a challenge. However, the positive point about taking a high tau value is that a sizable most of the non-defaulters, these non-defaulters will be classified as non-defaulters only. That means your false positives will be very less. So your false positives are very less, but your false negatives are very high if you are taking a very high value of tau or thresholding. Let's take another example where you take a very low value of threshold. Let's say tau value of 0.01, this kind of small value, or sorry, 0.1. Your cutoff will be from here. Now notice in this case, all the default cases you will correctly, and most of them you will accurately classify them as defaulters only. So most of the defaulters are accurately classified as defaulters. So the error on this side, the false negative error would be very less, because most of the all the defaulter where actual outcome is default are being classified as default only. But what about these cases which are non-defaulters? It seems that many of these non-defaulter cases now are being considered as default. That means false positive. So now we are high on the side of positive error. So our false positive is high while false negative is low. So as we can see, there is a trade-off. As we increase the value of tau or threshold, we make one kind of error while being good on the other side, and vice versa for the opposite case. That means if we take a very high value of tau, our false negatives are higher but false positives are lower. But when we take a very low value, our false negatives are lower but false positives are higher. So there is a trade-off. Now let us try to answer the question, which kind of bank would select what kind of value, or how this value would be selected. So let's take two examples. One, a very conservative bank that want to give loans only to very credit-worthy borrowers, and a very aggressive bank which wants some kind of expansion, make some new relationships, and therefore want to loan out in large volumes. So these two, let's consider two cases. A very conservative bank would like to select only and only very niche, very small number of borrowers, and therefore it would like to classify even a small risk borrower as defaulter, and therefore it would set a very small threshold. So in that matrix, in the diagram, it will set a very small threshold. So a large number of cases would be classified as defaulters, and therefore those that are selected, a very small population of loan applications will be selected, small proportion will be selected, and definitely these would be very credit worthy borrowers. That means this bank this bank is taking a chance. In order to select only most credit-worthy borrowers, it is taking a chance and classifying even the relatively safer ones into the defaulter category. The advantage is aligned to its objective. That means it will get only and only those applications as non-defaulter that are very safe. Contrast this to an aggressive bank strategy. That bank would like to give loan to most loan applications, and therefore it would like to reject only and only high risky borrowers. So it will select a higher threshold, probably on the higher side here maybe, so that those that are rejected it is very sure that these are definitely not the good ones. However, in this process, it is taking a chance that while some of the good ones, most of the good ones are getting selected, but there are some of the bad borrowers, not so good creditworthy borrowers are also falling in that list because of this high threshold value it has put, which is rejecting only some of the extremely bad borrowers. So some of the good borrowers are also, or not so good borrowers are also falling inside and get their loans accepted or approved. However, please remember this, the value of tau changes its interpretation if your case of y equal to 1 and y equal to 0 changes. For example, all our discussions we are considering y equal to 1 as the case, which is default, and 0 non-default. As soon as you change this interpretation, you take y equal to 1 as non-default and 0 as default, then the entire interpretation changes to the opposite side. So we said that if the bank was more aggressive, it wants to accept most of the applications, expand business, then it will take a higher threshold. A conservative bank may choose a very low threshold value. So this is the, in nutshell, what we understood. To summarize, in this video, we discussed the concept of thresholding. We noted that while the model, the logit and similar class of models on discrete choice variables or limited dependent variables model and give dependent variable in the form of probabilities, we need to convert those probabilities into binary outcomes or something like one zeros, yes, nos, and so on. We took an example of bank loan default and non-default application to explain the case. However, in order to convert these probabilities into ones and zeros, we need a thresholding or number, a cutoff range above which the values can be classified. If probability lies above in from that, we can classify it to 1, and if it is low, then 0. So we need a threshold number which can be used to classify. We also noted with the example of bank that there is a trade-off. Depending upon the value of tau, you have a certain probability of making error called false positives, that incorrectly classifying as ones, and false negatives, that means incorrectly classifying as zeros. And there is a trade-off between them which depends upon your selection of tau value. As a general rule, in the absence of any guidance, t equal to 0.5 is a good threshold, usually considered reasonable threshold.